In this video, I want to talk a little bit about skin repair. And when we're talking about skin repair, we're really also talking about how other tissues are repaired. So we will be bringing in some stuff from chapter 4 as well, where your book talks about tissue repair more generally. So I think we can all agree that a wound is a bad thing. A wound leaves you open to the environment. It's an access route for infection. So closing a wound is critical. There are two ways to close a wound. You can either have regeneration, which is replacing the lost tissue with the same kind of tissue, or fibrosis, which is another fancy way of saying a scar. A number of factors determine the balance between regeneration and fibrosis. Regeneration is really the ideal because scar tissue just isn't as functional as most tissue. So regeneration, replacing it with fully functional tissue, is the best thing. But whether regeneration occurs or whether you have fibrosis, it depends on the type of tissue and it depends on the severity of the injury. More severe injuries, of course, are likelier to scar. This whole process is initiated when inflammatory cells present in the connective tissue release inflammatory molecules, and these initial cells are called mast cells. Your textbook has a really great walkthrough of skin repair, and that's in figure 514. I'm going to be using it, I'm incorporating it into this video, and I've highlighted the most important things going on in each step. So this is step number 1 of skin repair, and that's, as I mentioned, initiation of an inflammatory response. Now, you may be used to thinking of inflammation as a bad thing, but inflammation also really sets the ground for tissue repair. It brings in immune cells that can attack and destroy any infectious organisms that got in at the wound site, and it also brings in the cells necessary to help clean out dead tissue, dead cells, and cell debris. This is a figure from chapter 4 that summarizes what happens during inflammation. You'll learn a lot more about inflammation when you study the immune response in the second quarter of Anatomy and Physiology. Inflammation is characterized by the 4 cardinal signs, which you're probably largely familiar with, even if you don't recognize the Latin names. Rubor is redness, calor is heat, tumor is swelling, dolor is pain. So redness, heat, swelling, and pain, these are all the cardinal hallmarks of inflammation. They come because of increased blood flow to the area. So part of the inflammatory response is chemicals that cause blood vessels to open up, so you get more blood flow, and that brings heat and redness. You also have the vessels become more permeable, so you get fluid from the vessels kind of leaking out into the surrounding tissue. This is important because that fluid contains cells, it contains immune cells, it contains molecules that may help with the clotting process or the stimulating regrowth. It also enables fluid to be swept into the lymphatic system, where that fluid can kind of be scanned for infection and targeted by the immune system. And then there are chemicals released during inflammation that actually stimulate pain-sensing neurons in the tissue, giving the condition of pain. Pain is another thing that you might be used to thinking of as a bad thing, but really pain is a signal to your body. Think for a second, what do you do when something hurts? You stop whatever you're doing. You're careful with the area that's sensitive. You protect the area that's sensitive. So pain is a message to you that you need to be careful with this area that's just been damaged. If the inflammation continues for a long period of time, or continues even after the wound has been healed and the infection has been cleared up, then chronic inflammation can really become dangerous and destructive. But in the short term, inflammation is a completely appropriate response to tissue damage. Okay, so you have one of the other things that happens initially when you have a wound is you have formation of a blood clot, and the blood clot kind of acts like an initial stopgap, stops bleeding, and kind of initially fills in the area. And you have formation of a scab as well, and scab is basically the dried portion of a blood clot, and it acts like a cap over the damaged area. So it protects the damaged area from infection and from further damage while the repair process is going on underneath. That's why it's important to not pick a scab off before the tissue underneath that scab is done healing. One of the earlier parts of the repair process is that you have epithelial cells migrating along the edges of the wound. So in the skin, these are cells of the stratum basale, the actively dividing cells. They actually divide, they increase their division rate and push cells out along the edge of the wound. Phagocytic cells that are being brought in by that increased blood flow and increased blood vessel permeability move into the blood clot, and they start getting rid of cell debris, damaged tissues. This tissue that is rich in blood vessels and rich in immune inflammatory cells is called granulation tissue. This is what granulation tissue looks like under the microscope. It is highly, highly cellular. All these little dark spots, those are the nuclei of cells that are in the granulation tissue, working to repair and rebuild. Granulation tissue also has a lot of capillaries in it that have grown into it to feed regeneration, to bring the oxygen and nutrients and cells and growth factors that are important to stimulate repair. You also see fibroblasts, and these are these cells here with much more cytoplasm to them. And fibroblasts, if you think back to studying the tissues, fibroblasts are the cells that make fibers in connective tissue. So they produce the extracellular matrix in connective tissue. So these fibroblasts, they are starting to lay down the basis for rebuilding the tissue that used to be at the wound site. Okay, so a while after the injury, the fibroblasts have been busy laying down a collagen fiber meshwork, and epithelial cells have been migrating along that meshwork, kind of regrowing the epithelium underneath the clot, as the phagocytes that are there are breaking that clot up and getting rid of it. After a while, the epidermis beneath the scab has completely reformed, and the scab falls off because it's not attached to the new healthy epidermis. The fibroblasts are still active. There may still be some scar tissue underneath that site. The amount of scar tissue that's left versus actually regenerating, as I said, depends in large part on the size of the tissue. You can think of regeneration versus fibrosis as being like a race. Like if regeneration can happen quickly enough, then it can take the place of scar tissue. But if regeneration can't happen very quickly can't happen quickly enough because the wound maybe is too big, or because it's tissue that doesn't regenerate well. Skin tissue regenerates quite well, which is what you would expect of tissue that is constantly being abraded and scraped and cut and constantly in danger. But other tissues, like the muscle of the heart, for example, they really don't regenerate very well. And in tissues that don't regenerate well, or tissues that have had a large wound, you get the scar tissue left behind, and it never really goes away. This is a comparison between scar tissue and regular tissue. It just shows how scar tissue is distinct from normal functional tissue. You have the normal functional tissue over here on this side. You can see how you've got that dense, irregular collagen fiber arrangement. You've got hair follicle. You've got a sweat gland deep down in there. Over here in the scar tissue, it's just a sea of collagen fibers. Scar tissue is very densely packed with collagen fibers, but if there's no epithelium in there, can't reform hair follicles, it can't reform sweat glands, can't reform sebaceous glands. It's not functional in the same way that normal skin is. It's also just not nearly as flexible. So you can get scar tissue if you have extensive scar tissue, particularly like over a joint. It can actually limit mobility at that joint. Tissues that have a high regenerative capacity are typically tissues that have a high division rate and tissues that have a good blood supply, good vascularization. Tissues that meet these criteria are epithelium, bone, areolar connective tissue, bone marrow. Smooth muscle and dense regular connective tissue is all right. Skeletal muscle and cartilage does not have a great ability to replace itself, very limited cell division. Skeletal muscle has very limited cell division, but has a great blood supply. Cartilage also has much more limited cell division. And then cardiac muscle and the central nervous system has little to no regenerative capacity. Really, almost no cell division goes on in the heart or the brain, very, very small amounts. And so it can't really replace itself. This is why heart attacks can be so damaging to the heart over time, because the heart muscle is replaced with non-functional scar tissue. And also why something like a stroke in the brain can really be debilitating, because the tissue that's lost can't replace itself. But tissues with a high regenerative capacity, as long as you are in good overall health, you have good nutrition, the nutrients that are necessary are present in your body, and you have good blood flow that's capable of getting to that wound, these tissues can be quite good at regenerating themselves. But it still depends on the size of the wound. If the wound is too large, you can still end up with fibrosis, winning out over regeneration. Alright, after studying this video, you should be able to distinguish between regeneration and fibrosis, talk about how important inflammation is to tissue repair, describe in general terms the process of tissue repair, and again, I direct you to that figure 514 in your text. Talk about granulation tissue, what that is, explain the factors that determine how well a tissue regenerates, and discuss why fibrosis is a less optimal outcome than regeneration. This is goes along with distinguishing between regeneration and fibrosis.